All right. So please, everybody, if you're watching this, be sure to log in before you do these problems so you get credit. I'm not logging in so that the answers aren't going to show, because on my account, I've done them all already. All right, we're going to recursion 1, and we're going to do the first 6. That's factorial through some digits. All right, so factorial. We already did this in in class. This will be slightly different. No, I guess it's pretty much what we did in class, and I even give you a hint. But let's just try to do it without looking at what we did before. So remember, every recursive function needs a base case and a call to itself. So I'm gonna say the base case. I'm gonna say the base case. If n equal 1, return 1. And then otherwise, we're going to return n times factorial n minus 1. I think that'll do it. This is, yeah. So if n was 3, it would first return 3 times and then call it with 2, and then it would say 2 times, call it with 1, and when it's 1, it returns 1. So we end up with 3 times 2 times 1. Anyway, we just checked it. Not too bad, not too hard. My advice is, on each of these, if you got the video going, just pause it and try to do it on your own before you just type in what I did. I mean, if you just type it all in, you're not going to learn anything. All right, we have a number of bunnies. Each bunny has 2 big floppy ears. We want to compute the total number of ears across all the bunnies recursively without loops or multiplication. So, I mean, obviously you could just take bunnies and multiply it by 2, and then that's the answer, but that's not what we're doing. We are going to instead do a little bit like factorial, except instead of multiplying by n, we're going to multiply by 2. So let's say if the number of bunnies that we're being asked to deal with is 0, we return 0. Otherwise, we're going to return 2. Each bunny has 2 ears plus bunny ears, bunnies minus 1. I think this will do it. Sweet. Yeah, so say we send over 2. It first calls this with 2, and it returns 2 plus, and then it calls it with 1, and the 1 returns 2 plus, calls it with 0, and then the 0 returns 0. So then it's 2 plus 2 plus 0, and we get the proper answer 4. I love that they tested it with 234 and they got 468. Oh, and they even give you a full solution. Let's see. Yeah, it's exactly the same as mine. So, all right, we're doing the first 6. So Fibonacci. Now this Fibonacci is slightly different than the Fibonacci that I gave you because they started at 0. I started mine at 1. There's different ways to do this, and I don't want to argue about whether Mr. Fibonacci was a 0-1 for the first 2 or a 1-1 for the first 2, because I don't know. Anyway, but we'll deal with those as our base cases. If n is equal to 1, we're going to return 0 because the first term is a 0. And if n is equal to 2, the second term is a 1. And then now we're going to return the sum of the previous 2 terms. So if it's not a 1 or a 2, those are the base cases. And in fact, we have 2 base cases. We're going to return Fibonacci n minus 1 plus Fibonacci g n minus 2. And I think that'll do it. We'll see. Oh, I made a mistake. If they send over a 1, we're returning a 0. That's this one. If they send over a 2, we're returning a 1. And then after that, we're returning the sum of the previous 2. And, oh, I'm not dealing with a 0. That's probably part of it. If n equals 0, return 0. Let's see if that helps. Am I supposed to not have this line at all? Yeah, there you go. All right, well, they're saying term 0 is 0, term 1 is 1, term 2 is 1, and so on. So I just overthought it. Oh yeah, they did say n equals 0 is the start of the sequence. So anyway, my bad. I didn't read the instructions. So if we want the term 0, then we return 0. That's this one. And if we want the first term, term 1, then we return 1. And then otherwise, we return the sum of the previous 2 terms. And then this works it all out. Okay, I'm going to go back here. We've done 3. We got 3 more. So we're going to do bunny ears 2. All right, we have bunnies standing in a line. They're numbered 1, 2, 3. Odd bunnies have the normal 2 ears, and even bunnies, 2, 4, 6, 8, have 3 ears because they each have a raised a foot. We're calling them, they're 2 floppy ears plus the foot. We're calling it 3 ears. So again, if bunnies is equal to 0, we're going to return 0. Then if we have to deal with odd or even. So if bunnies mod 2 equal 1, so odd bunnies have the normal 2 ears, return 2 plus bunny ears 2 bunnies minus 1. And then otherwise, so we don't actually have to do another if, because it's only going to get here if it was an even number. And if it's an even number, it's a 3. Because even number bunnies have 3 ears. There we go. So our base case is if there's no more bunnies, we return 0. That's how we get out of the recursion. And then otherwise, there we go. All right, next, we have a triangle made of blocks. Topmost row has 1 block, next row 2, 3, 4, like that. So if they're telling us that it has 2 rows, then we know we have a row of 2, and then we have a row of 1. So that's up to, pardon me, 3 blocks total. So again, we're going to have a base case. If rows is equal to 0, return 0. And then otherwise, return rows plus triangle rows minus 1. Sure that'll do it. And of course, we could do this without doing recursion. You could just do a for loop. But as we've said, everything you can do with recursion, you could also do with regular for or while loops and vice versa. But I just don't want to go too many. Sum digits is our last one. So given a non-negative integer, return the sum of its digits recursively, no loops. And they're telling us if you mod 10, you get the rightmost digit. So for example, 126 mod 10 gives us 6, the rightmost digit. And when you divide by 10, it removes the rightmost digit. So 126 divided by 10 gives you 12, because you remember this integer math, it doesn't give you a decimal. So for this, it's really the end case is when we get down to a number that's less than 10. So if if n, but I'm going to do it backwards. If n is greater than 9, then we're going to return n mod 10 plus some digits n divided by 10. Otherwise, we're going to just return n. Yeah, sweet. So let's talk about what I just did. If it's bigger than 9, that means it's a 2-digit number. So then we're going to return the rightmost digit. Remember this example up here, 126 mod 10 gives you a 6. And then we're going to call plus. We call recursively, call the function again, or the method again. This time we're lopping off that rightmost digit. So this will just keep happening. If it was a really big number, it'll just keep happening until it gets down to the last digit, which is no longer a 2-digit number. It'll just return that number because we're trying to add up all the numbers. That's where it goes. All right. I hope that helped. If you had a lot of trouble doing these, I've got some great advice for you. Come back tomorrow and don't log in. And if you're logged in, log out, and then try doing these 6 problems again without looking at your answers. It's probably going to be hard, I know, but it would be good to practice and be able to do things like this without watching my video or looking at your previous answers. Anyway, good luck. Thanks.